Welcome to the deep dive. Today we're digging into what feels like a central tension in machine learning.
Oh, absolutely. It's that classic divide.
Yeah,
Right?
the massive, just undeniable success of huge deep learning models on one side.
And on the other, the rigorous, sometimes computationally brutal necessity of traditional Bayesian methods.
Exactly. We all know deep learning is king when you have tons of data. But if you need to bake in prior knowledge, or, more importantly, get a real handle on your model's uncertainty, especially with small, tricky data sets, Bayesian is still the gold standard.
And that's the gap this paper we're looking at tries to bridge. It's called Transformers Can Do Bayesian Inference, and it introduces a concept they call prior data fitted networks, or PFNs.
Right. PFNs.
The core idea here, the real genius of it, is how they use the in-context learning that transformers are so good at.
Okay.
So normally finding that posterior predictive distribution is this numerically horrible task. You're doing iterative sampling, complex integration. It's messy.
MCMC chains running for a week. We've all been there.
We have. PFNs they reframe the whole problem. They treat the training data itself as one long input.
The context.
Precisely. The prompt, if you will, for the transformer. And by doing that, they managed to turn this incredibly hard posterior approximation problem into a standard supervised classification task.
So wait, if I'm getting this right, the transformer is learning the algorithm of Bayesian inference for a specific prior.
Yes, exactly that.
It's not learning one model from the data. It's learning how to produce the posterior for any data set that could come from that prior.
You've got it. It's meta-learning the inference procedure. And the real payoff, the huge benefit, is the speed.
A single forward pass.
Single forward propagation. Once trained, you get a full probabilistic prediction instantly. No more waiting for days or weeks.
Okay, let's break down how that meta-training actually works, because it really twists the whole idea of supervised learning. The paper's first figure really lays it out. You start with a strong inductive bias, a prior distribution over the kinds of learning tasks you're expecting.
Which is key.
Yeah.
The PFN needs that structure.
Then the training loop is, well, it's quite elegant. First, you sample a task, say a function, from your prior. Second, you draw a synthetic data set, D, from that function.
Inputs and labels.
Right. Third, you just mask one of the labels. That becomes your test point.
Your test.
And fourth, you train the PFN to predict the probability distribution for that masked test, using the rest of the data set as its input.
And that training is driven by what they call the prior data negative log likelihood, the data.
And this is where it diverges from something like variational inference.
Completely. With VI or MCMC, you're usually trying to approximate the posterior over some latent variables. PFNs just bypass all of that.
Yeah.
They model the thing you actually care about, the posterior predictive distribution, or PPD, directly from the data samples.
So what's the mathematical justification for that?
That's what they call Insight 1. They prove that minimizing this prior data NLL is the exact same thing as minimizing the expected cross-entropy between the true PPD and the PFN's approximation co-out.
I want to pause on that because that sounds like a huge deal for just validating the model. If you're minimizing the KL divergence, what does that practically tell you about the quality of the predictions?
It gives you an incredibly clean, principled metric for how good your approximation is.
Okay.
Corollary 1.1 makes it formal. Your loss function is, up to a constant, the same as the expected KL divergence between the ground truth PPD and your PFN's output. So when you see the loss go down, you know for a fact your predicted distribution is getting closer to the true Bayesian one, both in its mean and its uncertainty.
So it's not just getting the right answer, it's getting the right level of confidence.
Precisely. And Corollary 1.2 adds a nice theoretical guarantee. If the true prior is something the PFN can actually represent, then the optimal PFN will match the true PP perfectly. The whole approach is, it's sound.
The theory is sound, but you can't just throw a set of data points into a vanilla transformer. They're built for sequences. Order matters.
Right. And for a data set, order shouldn't matter. So they had to make some clever architectural changes.
They started with a standard transformer encoder, but then what?
The biggest change is what they got rid of. No positional encodings. At all.
So how do you combine the data points?
You just sum their encodings. The sire hairs get embedded, then added together before going into the self-attention blocks. It makes the model completely invariant to the permutation of the input data.
Simple, but effective. What about attention?
That had to be customized too. They use specific attention masking. So every training point in the input set can attend to every other training point.
Okay.
And every query point can attend to all the training points. But, and this is Critical query points are masked so they can't attend to each other.
Ah, so each prediction is independent. That makes sense.
Exactly. They also do a bit of clever engineering with the sampling. They oversample datasets with a larger number of training points,
No.
modelers.
Why do that?
It balances the training signal. If you have you have a lot of query points, so you get a lot of gradient updates from one sample. Oversampling large dollars just ensures that across the whole meta-training process, the model sees a balanced number of query points for different context sizes.
That's a subtle but important detail. Okay, let's flip to the output side. Predicting a continuous distribution is notoriously tricky for neural nets. They came up with something they call the Riemann distribution.
It's a really smart solution, actually. The idea comes from, of all places, distributional reinforcement learning.
Really?
Yeah. Essentially, the PFN outputs a bar plot, a histogram that represents the predicted probability density function.
A discretized distribution.
A discretized continuous distribution, yes. But the clever bit is how they define the bins of the histogram, the buckets. They aren't just evenly spaced.
How are they chosen then?
They're chosen so that each bucket has the exact same probability mass under the prior data distribution.
Oh, that's elegant. So the architecture of the output head is itself defined by the prior.
Exactly right. It connects everything back to the core Bayesian assumptions, and they prove in Theorem 1 that this approach is robust.
Which says?
That a Riemann distribution can model basically any well-behaved continuous distribution to an arbitrary level of precision. So for any tiny error margin you can name, you can find a fine enough set of buckets to get your KL divergence below that margin. It's guaranteed to work.
Okay, the whole mechanism is laid out. It's clever. The theory holds up. Now, the performance. They started with a sanity check, right? Gaussian processes.
Yes. GPs with fixed hyperparameters.
Yeah.
The one case where we can actually compute the true Bayesian posterior in closed form, the perfect testbed.
And the results?
They were, and I'm quoting, virtually indistinguishable from the ground truth. The means, the confidence intervals. The PFN just learned the GP posterior predictive distribution correctly.
It passed the sanity check.
With flying colors. And they showed that the more meta-training data they used, the closer the PFN got to the optimal performance of the exact GP. The approximation just keeps getting better.
That's the validation. But the really exciting part is where this goes next, the intractable problems.
Exactly. First up, GPs, but with hyperpriors. The moment you put a distribution over your hyperparameters, the posterior becomes intractable.
So they benchmarked the PFN against what?
Against maximum posteriori estimation, or MLE2, and
Yeah.
the gold standard MCMC sampler, nu T-cusp
Exactly.
stick. The PFN's approximation of the true PPD was far better than both. But here's the number that just jumps off the page. The speed up.
How?
PFN inference was between 1,000 and 8,000 times faster than Newt's.
1,000 times.
At least, and over 200 times faster than the already faster MLE2.
That kind of speed up changes what's possible. It moves these methods from a research curiosity to a deployment reality. They took this to Bayesian neural networks next, didn't they?
They did, and the results there are even more staggering. BNNs are notoriously slow, even with modern methods like stochastic variational inference.
Is by backprop SVI. Yeah.
The PFNs got the same performance, measured by their prior data NLL, using a tiny fraction of the compute.
Okay, give me the numbers.
The PFN was 1,000 times faster than SVI, and compared to running NUT on a BNN, it was 10,000 times faster.
10,000. That's not an improvement. That's a different paradigm.
It completely removes the primary computational barrier for using BNNs.
So how does this actually play out on real-world problems? They use the OpenML AutoML benchmark on small tabular data sets.
Right, with only 30 training samples each, which is a perfect use case for Bayesian methods.
And the prior they used here is really fascinating. It wasn't just over the BNN weights.
No, this is cute. It was a BNN prior over architectures. So the PFN was Bayesian over the number of layers, the hidden units, the activation functions, everything.
Which means you're basically integrating neural architecture search directly into the inference step. You don't have to do it separately.
You've completely eliminated the nest problem that's just part of the prior.
And the performance.
On the 20 tabular datasets, the PFN-BNN model came out on top. It beat strong baselines like XGBoost and CatBoost on average rank for ROC-AUC.
But the runtime must have been the real story.
Oh, it's night and day. Because it's just that one forward pass, the PFN-BNN took only 13 seconds to run on all 20 datasets combined.
13 seconds for everything.
For everything. XGBoost, with hyperparameter tuning, took 20 hours.
That's what is that, a 5,000x speed up on a practical benchmark?
About that, yes. And on top of that, the uncertainty calibration was better. It had a lower expected calibration error than the standard BNNs and even XGBoost.
They also hit few-shot learning on Omniglot
Yeah.
just to show the flexibility.
Right, and they used a really simple synthetic prior, just random straight lines, something that would be a pain to use in a traditional Bayesian setup.
But the PFN didn't care.
The PFN didn't care. You can sample from it, so you can train on it. After fine-tuning on Omniglot, it achieved performance right on par with state-of-the-art meta-learning algorithms. It just shows how general the framework is.
So, bringing it all together, what's the final takeaway?
I mean, the synthesis is pretty clear. Prior data-fitted networks are a simple, cheap, and very general way to approximate the post-year predictive distribution for a huge class of priors.
And you get these massive computational gains.
Massive. Factors of 1,000, 10,000 for intractable problems, while still getting high accuracy and, importantly, better uncertainty calibration than what we had before.
This feels like it opens up a whole new research area. The paper mentioned a few future directions.
Yes, and they're exciting, like exploring totally new kinds of priors that were just computationally impossible before, or designing new architectures specifically for PFNs, not just adapting transformers.
And, of course, scaling them up.
Scaling them up and using them for things like amortized simulation-based inference. The potential applications are vast.
So let me leave you with a final thought on this.
Given that PFNs effectively eliminate the need for per-dataset hyperparameter tuning, right, they can bake the choice of a BNN architecture directly into the single Bayesian inference step.
A tuning-free prediction.
Exactly. So here's the question for everyone out there working in meta-learning or AutoML. What are the real profound implications for all of our standard hyperparameter optimization routines if this one big upfront PFN training phase just replaces all future task-specific tuning?